For some reason you are not able to hear, please speak so that they're on the same page. So far, today there's no one speaking, so you must be very tired. Or very focused. Which one is it? So can you confirm that you can see the screen?
Yes, we can.
Yes, we can.
Good.
Yes, we can see.
So these slides are not in the best of shape yet, but I'm building them as we go along. Didn't have time to clean them up, but today we'll start with the change of basis as a topic. Let's explain what this means. So if you have this, we'll start with a small vector space, and we shall generalize the whole idea. If you start with R2, you can set up two bases, B1 and B2. So B1 has the vectors V1 and V2, and B2 has the vectors U1 and U2. So these are two bases for R2. That is possible. We saw earlier that there are infinitely many different bases for R2. So definitely you can get two different ones. So if you pick any other vector from R2, since B1 is a basis, it's possible to write any vector as a linear combination of the basis vectors. So we pick B1 first and write this vector V from R2 as a linear combination of our first basis vectors. And again, we define the coordinates as these coefficients. So the coordinates of V with respect to this basis are these coefficients, alpha 1 and alpha 2. So we shall denote the coordinates of a vector V with respect to a basis 1 with this notation. We have the square brackets and then the basis as a subscript. So this means the coordinates of the vector V with respect to the basis B1. Now remember, since coordinates are dependent on basis, what happens if you have a second basis and you wish to now convert coordinates in this new basis? In our case, we'll see how we can do that. How do you, if you have the basis, if you have the coordinates in one basis, how do you convert them to coordinates in a different basis? That's the target we want to achieve today. Okay, I think there are some people trying to join. Let me admit them. No, that's the wrong. Oh. So here we are. We have explained what is here. I hope there are no questions on what is going on, but just get this big picture. We are going to implement it bit by bit. So we use this. See, we have already written this vector V as a linear combination of V1 and V2. But now, since we can set up a second basis B2, this one U1 and U2, so it's also possible to write these basis vectors V1, since they're just vectors in R2, will also comply. It's possible to write them as a linear combination of these vectors in the second basis. So what you're going to do is we're going to write V1 as a linear combination of U1 and U2 and do the same for V2. And substitute them into this expression. So I assume this is a V1 written as a linear combination of U1 and U2. U1 and U2 are vectors. I should have made them bold. U1 here is a vector. The same here, U2 is also a vector in the second basis. So this again is V2 written as a linear combination of the basis vectors U1 and U2. So what I do here is simply put the like terms, pull out all the coefficients of U1 and put them together. So these are the coefficients of U1 grouped together, and then look for all the coefficients of U2 and lump them together, coefficients of U2. So this is what this next step does. That is simple algebraic manipulation, should not be hard for you to do. So that now we've been able to write this same vector V as a linear combination of U1 and U2. But now these two values, this first value and this second value, they make up the coordinates of V with respect to the basis B2. Okay. But now, if we look at this carefully, we can write them as a product of this matrix and these coordinates of V with respect to the basis B1. Because this is just the set of coordinates of V with respect to the basis B1. So we've been able to find a way to convert. We had the coordinates with respect to B1, and we have converted them just by multiplying by this matrix coordinates for B2. So I hope you still remember what coordinates are, because those definitions are really important to you. So this matrix here is what we call the change of basis matrix from B1 to B2. So the basis B1, the basis. So look at this carefully. I'll repeat what happened here again. We wrote U1 as a linear combination of U1 and U2. We also wrote U2 as a linear combination of U1 and U2. So if you look at this matrix, this B11 and B12, they form the first column of the matrix. B21 and B22 will form the second column of the matrix. So this is the matrix you're looking for. Once you have this matrix, you're able to convert coordinates of the V1 with respect to the V with respect to the basis B1 to coordinates of the same V, but now with respect to the basis B2. Sounded like someone is trying to join. Let's admit them. Okay, so are we together up to that point?
Yeah.
So now let's do a concrete example. We're going to pick two bases of R2. So the first basis consists of this vector 1, 0, 1, 1. Second basis B2 consists of the vector 1, -1, and 0, 1. So we have two bases. So let's pick a vector 8, 3 from R2. Now we can write this 8, 3 as a linear combination of the basis vectors in P1 as this. So V is the same as 5 times the first vector, 3 times the second vector. Here we are still at the basis B1. So the coordinates of the vector V, sorry, with respect to the basis B1 is this 5, 3. These are the coordinates. So I picked bases which are it's easy to guess the coefficients. But if you have something more complicated, you would you need to do some work before you get the answer. We can talk about the work later. So the other thing is we need to write each of these basis vectors in B1 as a linear combination of basis vectors in B2. So I will pick 1, 0 and find some coefficient beta 1, beta 2, give me a linear combination of these basis vectors in B2 that will result in 1, 0. So here we are. You can see that 1, 0 is the same as 1 times the first vector in B2 plus 1 times the second vector in B2. So we already get the first set of coefficients. Now the second vector in B1 is 1, 1. You can write it as a linear combination of the basis vectors in B2 again with the coefficients as 1 and 2. So now we can extract our, remember now these coefficients 1, 1 will make up the first column of our change of basis matrix. 1, 2 will be the second column of our change of basis matrix. And here it is. We've set it up. So let's illustrate now literally what the change of basis matrix does. Remember, we already have the coordinates of the vector 8, 3 with respect to the first basis. So the aim here is to change the coordinates to compute the coordinates of the same vector, but now with respect to the second basis B2. So we're going to use a change of basis matrix and the coordinates, the first, this first set of coordinates do that. Multiply the change of basis matrix by this first set of coordinates to give us the coordinates we are looking for with respect to the second basis B2. So our matrix, we called it P. I've avoided the fancy notation. You can put notation to show that you are shifting from B1 to B2, but I've left it out. So if you want the coordinates of the same vector, which was 8, was it 8, 8, 3? The coordinates of 8, 3 with respect to the first basis was 5, 3. If you multiply it by this change of basis matrix, we'll get the coordinates of the vector with respect to second basis. And that we get 8, 11 as the coordinates. We can confirm if they indeed they are the coordinates by checking. So if you multiply 8 is the first coordinate, so multiply it by the first vector in B2. 11 is the second coordinate, multiply it by the second vector in B2. And you will see that you end up with the same vector 8, 3 that we started with. So now it has different coordinates with respect to second basis. But we're able to reconstruct it once we have the coordinates. And then this has enabled us to shift from the coordinates in one basis to the coordinates in another basis without having to recalculate the coordinates in the new basis. Once you have the change of basis matrix, do that. This can be reversed as well. You could actually work this inverse. The inverse of this change of basis matrix now will reverse. It will be the change of basis matrix from B2 back to B1. Are we together up to that point? Leo mmeamua muongee hata kidogo.
We are following through.
We together.
Following closely. Good. So let's generalize this to Rn. So suppose you have vector space Rn. Again, it's possible to get two different bases for Rn. The first one consists of the vectors v1 to vn. The second one consists of the vectors u1 up to un. So you have two different bases for Rn. You can get any vector in Rn and write it as a linear combination of the basis vectors in the first basis. So the coefficients now become the coordinates of that vector with respect to the first basis. So the aim now is to see how do we, is there a way we can convert these coordinates to coordinates with respect to the second basis consisting of the vectors u1 up to un. So the first step is to rewrite the vectors in B1 as linear combinations of the vectors in B2, and that's what we do. The next. So you see each vector that appears here, this B1, you replace it with this linear combination of the vectors in B2. That's what we do at the next step. So we replace each of these vectors V1 with linear combination of the basis vectors V2. So you'll see that in brackets. So like this first one is V1, this second one is V2, and so on. And this continues until you get to the last vector, Vn. So you can see the dots mean that this keeps going on and on until you get the last vector, Vn. So again, you put the like terms together, all the coefficients of U1, add them together. This is what you get, and then you multiply them by U1. Do the same for all the other vectors all the way up to UN. Just pick the coefficients of like terms and add them, then you group them. So now this will be a linear combination of the same vector V, but now as a linear combination of the basis vectors in B2. So now we found the coordinates. These are the coordinates of the same vector, but with respect to the second basis. So we can collect them and put them this is incomplete. This is supposed to, I think this one is from the older one. This is only for R2. It's supposed to extend to Rn. So this is supposed to extend all the way to n terms and also going down total of n coordinates. If you check here, you will see what I mean. This will be the first coordinate, the second coordinate, keep going in the same fashion until you get to the last coordinate here. So this is the first one, second one, there will be a third, fourth, and so on until you get to the n coordinate. So there should be a list of n terms, not 2. Correct that. So this should be n of them. And if you check carefully, these coordinates can be obtained simply by multiplying this matrix of coefficients, with the coordinates of the same vector with respect to the first basis. So now what will happen here is that you will get coordinates with respect to the second basis. And this matrix you have here will be your change of basis matrix. This is the matrix we labeled P. That becomes our change of basis matrix from B1 to B2. So it can be shown that this change of basis matrix is invertible, and its inverse is the change of basis matrix in the reverse order now from B to B1. So that's the general form. So the only thing we need to fix here is that this term needs to be generalized. It's not generalized. This one is still carried over the term, the case when we were working with R2, that we need to generalize it to Rn. So we'll fix that. Is this making sense? So when you're doing things like principal components analysis, usually you are changing basis from a bad basis to a good basis. That's usually the idea. We shall encounter that as we do the applications. So the next thing we'll look at is similarity. So we say that two matrices are similar if we can find an invertible matrix P, like that A is equal to PB, P inverse. we've already seen an example of similarity where when we do diagonalization, we find a diagonal matrix which is similar to our original matrix. So there's some similar matrices. We should try to quickly make sense, or you still want them. Make sense as there, or you need some clarification?
Yes, please clarify.
So let me write down similar. So if I get the first, what was the first thing? It says the determinant of A matrices are similar, they have the same determinant, right? This is the first statement we had there. So it's easy to see this because if I get a determinant of A on this side, determinant of A, this is simply the same as, since this is a product of matrices, I will simply multiply out the matrices because that's a property for matrices. If you get the determinant of a product of matrices, the same thing as getting the product of individual determinants. So times determinant of B times determinant of P inverse. But the determinant of P inverse is just the same as 1 over determinant of P. So I can cancel this. These are just numbers, so I can cancel them out. They will disappear. So I'll be left with determinant of B. So this shows that if two matrices are similar, then they have the same determinant. So that should be the next one. The next one says a trace of A is the same as trace of B. So if you have a square matrix, if A is an n by n is a square matrix n by n, we define the trace of A equal to the sum of the elements in the leading diagonal. It means those are just the elements which AI, where I will AII, where I will run from 1 up to n. So this gives you the trace of a matrix. You just sum the elements in the leading diagonal. So for example, if I have 2, 1, 1, 4, the trace of this matrix will be what? If this is A, what will be the trace of A? If to write it out like this, the first entry is A11, A12, A21, A22. So you notice this sum for the trace simply picks the entries which have the same index for the row and column. So I, that will just be these entries in the leading diagonal. So in this case, the trace of A will be 2 plus 4, which is 6. So this works for any square matrix. You simply add the elements, the leading diagonal, and that gives you the trace of the matrix. Again, this will be useful when we are working with the covariance matrix. The trace of that covariance matrix simply gives us the sum of all the variances. Then the concept of similarity and this trace of two similar matrices the same. So the other thing, what you can use here to solve this problem, will this, but you can show that the trace, if A and B are square matrices, then the trace of the product of A and B is the same as the trace of the product. If you reverse the order, the trace, you will not lose the trace. The trace will still be the same, as long as the square matrices. This is okay. Are we together? So we can say that the trace of A same as the trace, since A can be replaced by P, P inverse. This is true. So you can pick this as one matrix, and this is a second matrix, and reverse the order. Reverse the order of the product, trace doesn't change. So this is still trace of P inverse. P multiplied by B. So remember, I told you I've treated this as one matrix, this product, and this as a second matrix. So I revise the order of the product. The trace does not change, but I get some new information here. This is just the identity matrix. If I multiply B by the identity matrix, I still get B. So this again confirms that if two matrices are similar, the trace, we have the same trace. Zile zimebaki mtamaliza wenyewe sasa, kama mnaogopa.
Maliza tu.
No, the teacher is supposed to do 25%. You want to eat into my share, man? Okay. So the next thing we said again, if two matrices are similar, they have the same eigenvalues. The eigenvalues of A this is just shorthand for eigenvalues. I'm a bit lazy. So we claim that the eigenvalues are the same. For A and B, if they are similar. So again, if A and B are similar, it means this property must hold. We can find an invertible matrix P such that PB, P inverse is equal to A. So how do we get the eigenvalues? Get the eigenvalues of A, we normally solve, set up this matrix, then we get the determinant and equate to 0, and usually we end up with a polynomial of degree n here. So we can just replace A, this PDP inverse. So it's the same as determinant of P minus lambda I. Now I can replace I think this is the correct order. This doesn't work, you just reverse the order, it should work. So this is the determinant of this matrix in here. Now this matrix in here, if you look carefully, P is lambda is just a scalar. So the scalar can be ignored. This matrix can jump to the other side, there's no problem. So P is common on the right-hand side. Then you multiply it on the right side, you have B minus lambda I. Then P inverse is common on the left-hand side. And you're getting the determinant of this matrix. So again, if you're getting the determinant of this matrix, I can get it out this way so that I think now if I use this second notation, X might look a little better. Or not necessarily, I can just use the bars. So you can write this as the determinant of P, since you are multiplied by the determinant of B minus lambda I. But now multiply by the determinant of P, which is the same as 1 over the determinant of P. So again, these will cancel out. These two determinants, you are left with only the determinant of B minus lambda I. So this is the same polynomial that you will use. This is the same characteristic polynomial. It's equal to L minus lambda I, because that's where we started. L minus lambda I is equal to this thing. And we have shown that this determinant is equal to the determinant of B minus lambda I. So since they have the same characteristic polynomial, those polynomials have the same roots. So it means the eigenvalues of A and B must be the same because they have the same characteristic polynomial. This determinant is a polynomial and it's equal to this one. So they have exactly the same characteristic polynomial, and therefore we can conclude that it's the same.
Excuse me, please let some people in the class.
Yep.
There are people waiting.
Came in silently. And then I will use that. If anyone is not attending class, I think I will not keep them in the data camp. I only want to keep people who are attending class. Nine today. So these two others, just take them as the proof for this one involves some concepts which I don't want to go into. This last one, you need to, you may have to connect this to linear transformations to prove this last one. I don't want to do that. This other one is connecting the similar, they have the same ring. This follows from the fact that the rank of a matrix is invariant to multiplication by an invertible matrix. Matrix by an invertible matrix, then its rank will not, the rank of the product will not change. It's the same as the matrix itself. And since we are, to get A, we are just multiplying B by invertible matrices, the rank will not change. All that can be proved, but don't need the details now. Which has more details. You can, if you want to get to the nuts and bolts, go to the textbook I shared. Another property that is useful is this one. It's used. This can be useful when working with the Markov chains. Things like population dynamics and so on. Also useful in systems of differential equations. I don't think we'll look at that, but it comes in handy there. Let's see why this is the case. So the claim is the following, that if we are claiming that if A is equal to P P P anything to the matrix P, I only get powers of B. So if this is true. So maybe the best way is to try it out with a small example. So suppose you want to get A squared. A squared simply means you multiply this by itself, right? So let's do that. Multiply A by itself, which will be P inverse multiplied by itself, will be P inverse. So these two matrices, once you drop the brackets, these will give you the identity. P inverse and P will give you the identity. And then what do you have left? P multiplied by B, which is B squared P inverse. So you can, if you keep doing this, so if you want to get A cubed is the same as A squared multiplied by A. So this is A squared multiplied by A, which is P. So you can see this middle term keeps collapsing. So again, you are left with P cubed P inverse. So again, this is useful for getting powers of matrices. Now, what's even better is if you diagonalize. So suppose you find an orthogonal, not necessarily orthogonal, even just this diagonal matrix diagonalization. Suppose you find a matrix which is similar to A. Then the good thing about diagonal matrices, let's try it with a small case. So if I have A is equal to diagonal matrix where I have 2 here and 3, 0, 0. So if I want to get A raised to N, it's very easy in this case. The only thing I have to do is to raise 2. That will give. You can try this with small values of N to convince yourself. So this is how I get powers of A raised to N. So it might be very hard for me to get powers of this matrix as it is. But if I've done this diagonalization, then it's easy. If I want to get A raised to N, then this becomes very easy. And we have the here, which is similar to A. So once you have diagonalization done, then this becomes easy. Because now getting powers is just as simple as getting powers of the elements in the diagonal. Then P and P do not move. They remain the same. So this can be useful in solving matrix recurrence relations. You can solve these predator prey systems. Quite a number of things you can do with this. The Markov chains and so on. So I think that makes sense. So now we singular value decomposition. I think this might be the last topic we are doing today. I think so. So it turns out that this diagonalization, this eigen decomposition of a matrix is not possible for all matrices. For some matrices, for example, if you want real eigenvalues for a rotation, where is this? So, for instance, if your linear transformation is a rotation, it will also be represented by a matrix. So if you want to get the eigenvalues for that matrix, it will be a bit difficult, because if you rotate a vector through an angle theta, it changes direction. For instance, if I want this vector AV to be a multiple of V, the best I can do is change the scale. I can scale it, but I can't change direction, right? But a rotation will change direction and will not scale the matrix. It will keep, so it won't be in the same direction. You come on and put on top. So you will not be able to get real eigenvalues for this matrix that represents this rotation. So it doesn't always work. There are also other matrices which don't have n distinct, because the other thing is usually we can compose a matrix which is similar to A. So this can be done, but this only works if the matrix A has n distinct eigenvalues. So not eigenvalues, eigenvectors. It's possible to have fewer eigenvectors, but still have n distinct. Fewer eigenvalues, but still have n distinct eigenvectors. So it only works when this is true. Now, this doesn't happen for all matrices. There are some matrices which won't have n distinct eigenvectors, and when that happens, you'll not be able to find an invertible matrix P which diagonalizes A. So this decomposition fails and pushes us. It also only works for the other thing it does, it only works for square matrices. This eigen decomposition only works for square matrices. So what if your matrix is not square? What happens? So that's where singular value decomposition comes in, usually known as SVD. So what does singular value decomposition do? It works as follows. It assumes that anytime you have a matrix A, so the assumption is this matrix is an M by N matrix. For now, we shall assume that M is greater than, it can work either way, but for the meantime, let's assume M is greater than or equal to N. So with that assumption, we claim that it's possible to decompose A into product of three matrices. The first matrix is called U, and this U is supposed to be M by second matrix will be, they usually use the symbol sigma to represent it. So this will be a matrix which is mostly zeros, but with possibly some non-zero numbers across the leading diagonal. This matrix is supposed to be M by this matrix VT. So this last one should be an N by N matrix. This is a transpose of V. So these matrices, U is and V, are supposed to be orthogonal matrices. So the claim is that this works for any matrix. This one does not discriminate. It even goes a step further. Matrix does not have to be square. You will find this decomposition. So U and V, we conclude, we claim rather, are orthogonal. What does orthogonal mean? It means that if you multiply U by its transpose, you will get the matrix. Same is true for V. So V and V transpose will give you the identity. So these are the for this decomposition. So I'll give a small hint on why this is the case. So the following happens. Anytime you multiply a vector, two things that happen. You change the direction, to change. If this was the vector V, then the image is blue. Assuming there's a matrix that acted on V, move it to W. Now we are working in 2 dimensions. So let's create a assume V, this V is also a unit vector. So the magnitude of V doesn't have to be, let's assume it is 1. Convenient for us. So A acting on V will give me a new vector W. W is a multiple of an vector. So let's call this W hat the unit vector in the direction of V. So this small vector here is a unit vector in the direction of W. A acting on V will give me a multiple of some other unit vector. So this tries to generalize the idea of the eigenvalues. Remember, the eigenvalues work like this. AV equals to lambda V. So here, the only thing that happens is that the vector is stretched. It doesn't change direction, it's just stretched. It goes in the same direction. This one does 2 things. It will take care of the rotation and also the stretching. So the matrix does 2 things. It will rotate and stretch. So the stretched can either be increasing in length or reducing. So basically, this is what the singular value decomposition takes advantage of. So what happens is you can pick a basis. If you're working in R2, a basis containing the vectors V1 and V2, and then you can assume that this is what happens. V1 is turned to a multiple of some other unit vector, V1. You can also pick V1 to be a unit vector, and you can also pick second vector. Suppose you're working in R2, we'll just stop at V2. So this will be sigma 1 U1, and this second one will be sigma 1 U2. Remember this is whose first column is V1, second column is V2. Other end, this matrix whose first column, when I write this vector makes up the first column of the matrix. So I've not written the matrix in full. This should be a 2 by 2 matrix. So V1 has 2 components, but since we picked it from R2, this first column will have 2 elements, the second column will have 2 elements, but this is shorthand for that. U2. Again, this vector has 2 elements. So again, this is a 2 by 2 matrix. Then on this other end, you will have sigma, which will be a matrix whose diagonal elements are just sigma 1, sigma 2. So this is a matrix that is called sigma. Write this. This is sigma 1. This is sigma 2. So this matrix here is what we call sigma. So now you have a matrix here, V. So you can choose V1 and V2 to be an autonomous matrix. Columns of the matrix V are just these vectors, V1 and V2. Matrix U, capital U, multiplied by sigma. So that's how it works out. So with this is a geometric understanding of it. Now, remember, you can select these basis vectors to be orthonormal, and if you're orthonormal, this matrix V will be the matrix V is going to be, what do you call it? It will be an orthogonal matrix. So if you multiply by the transpose on both sides, this V now will be an orthogonal matrix if you choose the basis to be an orthonormal basis, and that is possible. You multiply the side again, transpose. So this is just the identity because we chose an orthonormal basis. V will be an orthonormal matrix, an orthogonal matrix, so that V multiplied by its transpose will give us the identity. And on this other end, we have the decomposition that we wanted. So this is always possible for any matrix, whether it's a square or a round. Here we have used a square matrix as to illustrate the point, but this happens whether the matrix is square or not square. So are we together up to that point?
Yeah.
But this doesn't look clear. We shall now, there's a way now to compute U and V. We shall get back to that shortly, but let's look at examples that have already been computed. So this is just repeating what I have said. So here is an example of a 3 by 2 matrix. So the decomposition would look something like this. So this is a 3 by 2 matrix A. This will be matrix U, which will be 3 by 3. That is a big matrix U.
I have a question, if you don't mind.
This one is sigma. This is transpose of V. That's a setup. look for. So these matrices are the ones we are going to look for. It's an
Mbona
example of 3 by 2. So someone has a question, yes?
umehanga? Ulikuwa wapi nikikupigia pigia? Ulikuwa wapi vile nimekupigia sana?
This
Sorry,
your microphone.
Na simu
Wamboi,
yako kwani?
you are making noise for everyone.
Simu yako ina vibratingi unasikianga.
anyway, may I ask my question? Hello?
Can you hear me?
Oh yeah, I can hear you. Your voice, you keep disappearing. But anyway, my question was between you say that U and V are orthogonal to each other.
Yes.
But when I check the elements, sorry, I wanted to ask on which inner product space are they actually orthogonal, because U is an M by M matrix, meaning that it has M squared elements, and V is an N by N matrix. So
Two matrices are
they're not on the same space.
matrix. I think you haven't understood the definition of an orthogonal matrix. So this is what it means. So A is orthogonal. If a matrix is orthogonal, it means if I multiply it by its transpose, I should get the definition of orthogonal, right?
Oh no, not that. If you scroll upwards in this, just scroll upwards here. Oh, there. Okay. So here, when you mention U, V are orthogonal, that's what you meant, that they're orthogonal to each other, like to their transpose.
No, they are not orthogonal to their transpose. They are orthogonal matrices. An orthogonal matrix is defined as this: a matrix whose inverse is the transpose.
Okay. I thought that you were referring to both of them being orthogonal to each other over the same space. It's okay.
When we talk of orthogonal to each other, we usually refer to vectors.
But even like if you consider a matrix in R.
For instance, these two vectors are orthogonal to each other because their dot product is 0. We talk of vectors being orthogonal to each other, but when you say a matrix is orthogonal, what we mean is that if you multiply it by its transpose, you will get the identity. That's what it means to say that a matrix is orthogonal.
Okay, so how about the matrices? Let's say the standard basis for, let's say, R2, for example. If you consider those just any there's two in the basis, so would you say that those matrices are, if we just consider the inner product space over that, is it a valid statement to say that they're orthogonal?
The inner product space is over the vector space R2. Now, if you want to take orthogonality of matrices, now you have to define an inner product on the matrices.
Okay.
So now you have to move to a different vector space where the vectors are the matrices.
Okay.
So much to cover. We are mixing up issues. We are working in R2. We defined clearly what orthogonal vectors are. Vectors are orthogonal if just the usual dot product is.
No, I was not talking about R2. I was talking about the R2 by 2, for example, the matrix space R2 by 2. There's standard basis for that one.
So matrices.
Yeah, the M2 by 2 over the real space.
Yes, that is a vector space, but we are not interested in it as a vector space now.
Yeah, but that vector space consists of matrices.
So I think if you start a discussion, it's important that you respond. You don't disappear.
So we couldn't hear you for a moment.
Huh? You can't hear me.
I thought I'm the one who disappeared. Sorry. So,
So,
No, we couldn't hear you for a moment.
so can we clear the air now? What do you understand when I say orthogonal matrices? What do you understand?
well, you've just explained that when you take the inner product of a matrix with its transpose, you're supposed to get the identity matrix.
So this is not the inner product.
Sorry, the dot product.
Yeah. This is not the dot product. This is just a product of two matrices.
Oh, sorry, yeah, sorry, the product. Okay.
When you talk
In
of
that
dot
case,
product,
then I had it wrong.
pardon?
In that case, then I had confused something. Sorry.
Okay, so you have to be very careful with the terminology here. It's a lot of work. That's why I kept saying you have to make sure you read regularly everything from the beginning. A lot of these concepts look simple when they're being explained until you try to write them down yourself. So you need a lot of practice for them to stick. So I'll repeat again. If we say a matrix is orthogonal, if this product, if its inverse is a transpose, that's all. The inverse of a matrix is a transpose, then the matrix is orthogonal. Now, two vectors are orthogonal if their dot product is 0. So when you talk about dot product, you need two separate vectors. And then the other thing you talked about inner product. If you're getting an inner product of two vectors, your answer should be a number, not another matrix. So this cannot be an inner product. So I have avoided all other vector spaces. There are many other vector spaces you can work with, but I don't need them for this course. If we had enough time, it would have been possible to cover them. They are like you can work with polynomials, they are vector spaces. You can work with some continuous functions, they are also vector spaces. It's a very wide topic. So focus on what we need. I suspect you may have read this somewhere else, and you have mixed up the issues. But it's fine. It's good. Anything that's confusing, please don't hesitate to ask. But make sure you get the definitions very clearly. So I will also try to be a little less casual when I write down these terms so that there is no confusion going forward. So where was I now? We were back to the slides. So I don't know whether we should take our usual 10-minute break now, or we.
Yes, you should take the break now.
Okay, so we take the break, then we resume at 8 o'clock. So you can use the break to review your notes. If you are not tired, if you're tired, just rest. we can continue now. Here we're looking at some examples how this decomposition will look like. So here we have a full decomposition of a 3x2 matrix. We have our matrix U, X sigma. It's on this side. This one is back on the phone again. And, okay, I've muted her. So this is what it looks like. Basically, it's just good to get the visual so that you figure out. You should be able now to similar visual for different sizes of matrices. So that's for a 3x2 matrix. This is the same 3x2 matrix. Something I was supposed to leave out, but I have not. Let's see. This something I was supposed to cut out here. I have not cut it out. There is something called the thin singular value decomposition. So this first version I showed you was a full singular value decomposition. This second one is supposed to be a thin singular value decomposition. That works in full. Sigma matrix because it's just zeros. So this column and this row will not contribute anything to the final, even if you drop them. If you drop this column, 3x2 here, sigma sort of 2x2 matrix here, you still get it would still work. So this one is called the thin singular value decomposition or economy. Some books call it differently, but thin is common, the thin SVD. So we will do that later. So you see the actual, what actually happens. So now the other way we could these vectors in this matrix U are called the singular vectors, left singular vectors, these ones. So these columns of the matrix U are called the left singular vectors. And also the columns of the matrix B called the right singular vectors. We'll see how to get them. And then these values here are called the singular values, sigma 1 and sigma 2. So we can rewrite this, we can expand this as a sum of rank 1 matrices as follows. First thing we do is pull out the vectors. So this U1, U2, and U3 are the singular vectors that make up the U. It's possible to set up this. You can have can rewrite this matrix as a sum of two other matrices.
I think we didn't get you clearly.
You can't hear me?
Yeah. Can maybe go to the previous slide.
What part did you miss? You know, you have to be a little more specific.
Yeah, I think we lost your connection from this point.
You can hear me now, though.
Yeah.
Okay. The connection is on. Maybe it's just weak. I don't know. Looks full. Everything is okay, but not sure what is going on with the connection. But if you can hear me now, I think that's perfect. So what is happening here? These U1, U2, and U3 are simply the vectors that make up the columns of the matrix U. So we just pull them out as vectors. And then these other two vectors, V1 and V2, are these columns for the matrix. This is not, this is V transpose. So you have to think of V. So these are the columns that make up V. This is V transpose. So we are not looking at this. So the V1 is this first column. V2 is this second column. So we can write out the whole matrix. This expansion can be written like this: sigma 1 multiplied by U1, V1 transpose, sigma 2 multiplied by U2, and V2 transpose. So this will be matrices of the same size as A. U1, V1 transpose will give you a matrix of the same size as A, but it will be a rank 1 matrix. So the other thing we normally do, these singular values are written in descending order. So sigma 1 is the largest, sigma 2 is the second largest, and the last one, sigma n, will be the smallest. So sigma 1, they are usually ordered in descending order. So that means you can get an approximation of A as follows. Here you have, this is the first approximation. So if you ignore the second term, this becomes an approximation of the matrix A. Here it happens that there are only two, so maybe the approximation won't be so good, but if you have many terms, usually works out well as an approximation. So this second one also, if you include both terms, you get the exact matrix A. But if you just pick up some of the terms, in this case, you can only remove one because there are only two. So this will give you the first approximation of A, the matrix. So so the smaller the values of sigma, the less important those terms are in this expression. So if you think in a more general case where you have an m by n matrix, this expansion can move to more than n vectors, more than 2 vectors. So if you have a total of n vectors, n eigenvectors, then you can set this up. You'll stop at n because remember we said m is bigger than n. So n is the smaller of the two. So you have to stop at n. And this is now the expansion of an m by n matrix, where U1 is just the U1 up to UN are just the left singular vectors that make up the matrix U. And V1 up to Vn are also the right singular vectors that make up the matrix V. So this is repeating what I was saying earlier. The singular values are put in descending order. And therefore, if you just pick some of them, so suppose you pick only R of them where R is smaller than N, then you can get an approximation of a matrix A using this expansion. Each of these is a rank 1 matrix. So this becomes more useful if you're working with the higher dimensions. In the first case we looked at where we have only a sum of 2 terms, then it's not very useful. But when you have much higher dimensions, then this approximation now becomes useful. And sometimes you'll find that the first one or two terms are really big and the rest are small, and just the first few terms will be a good approximation of the matrix A. So this is how, this is not the most efficient way to compress a matrix. There are other better ways, but this one serves its purpose as well. But since things like images are just matrices, and you can use this to compress an image, we will see that at some point during the applications. So here is an actual example that is worked out. We have a 4x3 matrix. So we have a matrix U here, which was obtained. We have the matrix sigma. Then we have the matrix V transpose here. I hope I wrote this correctly. Sometimes when typing these things, you can be crazy. So if you multiply out these three matrices, you should get your A back. Now this one, if you split it into a sum of, now what is happening here is we are getting this expansion. See this expansion? But now for a concrete case, so we identify this is a U1 and this is V1 transpose. This is U2 and this is V2 transpose. This is U3. This is V3 transpose. Same way we defined them earlier. And these are the singular values, 2, square root of 2 and 1. You can see they're in descending order. 2 is the largest, followed by root 2, followed by 1. So I can get an approximation of A by dropping either the last two or just the last one. So I could drop this last term. I still get an approximation of A. Or I could drop the last two. If this approximation was good enough for me, I would just drop the last two and remain with the first one. But here I think you may still need, I haven't checked how good an approximation it is. So, but this just illustrates the point. Now these approximations are easier to check with the computer. So when we're doing the actual computing, we'll be able to do some checks on how good an approximation is. So when you expand, what happens if you multiply this matrix, this vector by this vector, or that matrix, whichever you prefer to call, this is what you'll get. You're multiplying it by 2. We do the same for the other 3 terms. So this, if you add this up, you will see that you get, you recover the original matrix. Or do you? You need to double check. So if the multiplication is done properly, if you add these up, you should recover your original matrix. But you can approximate A by dropping maybe the last term or dropping the last 2. So this is a thin SVD where you can drop some columns of A of U. We had U was a 4x4, right? So you can drop the last column. You see this, if you check sigma, this last row here is 0. So we don't really need it. This last row and this last column of U, they don't contribute anything. If you look through the matrix multiplication, for instance, if you're multiplying this first row by this first column, this last term will just be multiplied by 0. The same happens for all the others. If you multiply this by that one, this last term will just be multiplied by 0. So this last column is actually in the kernel of the column space. So it's mapped to 0. So this you can drop this column. You can also drop this row, and all will still be fine. Then you get the thin decomposition. This one. We have dropped the last row, which was full of zeros. Then we have dropped the last column here, which doesn't contribute anything. So now you have a smaller representation, but it gives you exactly the same answer. So this is what you call the thin SVD. The first one was the full SVD. So what process do you use to obtain this singular value decomposition? Maybe now the best way is to go to the board. So the claim is this: we want a matrix that behaves like this. Then we put some conditions on U, as well as we want this one to be an M by M matrix. We want this to be M by N. We want this to be as N by N matrix. Now the assumption is that M, the initial matrix, is M by N. So when you multiply this out, you should get the initial. Now if you want to get V, the first step you will do is to multiply A transpose by A. Is that okay? So we get A transpose A. So I will use some properties of matrices. Suppose I have 3 matrices. It's A, B, and C. I multiply them. If I to get their transpose, the transpose will simply be the same as, I can now rewrite the same matrices but in reverse order and get each individual transpose. So I'm writing them in reverse order. So this is true for transposes of the product of matrices. So this is the same as this. I'm going to apply this now. So here we have a product of 3 matrices. So if you get the transpose of this, you'll have to rewrite this as V. The transpose of a transpose is just V. So you recover the V if you apply the transpose twice on this. And the sigma transpose, then U. I think U transpose, yes. So the other thing we need to do is multiply A. So we've gotten the transpose of A, we can multiply A. What do we get? A will be U sigma V transpose. Now we already said that U is an orthogonal matrix. So if I multiply U transpose by U, I will get the identity. So I can drop this middle part. Then I will have this as V sigma transpose multiplied by sigma. Then this is V transpose on this other side. So eventually this will now be an N by N matrix. Everything will be N by N. You can check the dimensions later if you want to confirm. You can just follow the multiplications and keep track of the dimensions. Now, when you multiply this, you will get a diagonal matrix. I will call it D. These two, they will give you a diagonal matrix. Maybe at some point we'll look at an example where it happens, but for now, that's what will happen. So we'll be trying to write A transpose A like this. Now, anytime you multiply a matrix by its transpose, it doesn't matter what matrix it is. If you multiply matrix by its transpose, what this will result in a symmetric matrix. It will be symmetrical. And we saw earlier that if a matrix is symmetric, then it's always possible to get to diagonalize it orthogonally, to get the orthogonal diagonalization. So this will just be a square matrix, which is symmetric, n by n. And this is the orthogonal diagonalization of this square matrix. So if I get the orthogonal diagonalization of this square matrix, I will be able to find my vectors V. So these vectors V will just be the eigenvectors of this product A transpose A. This is a square matrix now. I can get its eigenvectors. And this diagonal matrix will just be the eigenvalues of this product A transpose A. So remember earlier, we said how this works is we are looking for this kind of transformation where A multiplied by the first element is equal to sigma 1 U1. Sorry, U1. So these are vectors. V1 and U1 are vectors. Now, if I want to get U1, so this means I can get U1 as follows. U1 will simply be, I multiply both sides by 1 over sigma 1. Multiplied, I get the matrix A multiplied by V1. So once I obtain, this diagonal matrix will contain sigma 1. The diagonal matrix will contain sigma 1 squared, sigma 2 squared. They will be squared because when you're multiplying these two, the diagonal elements will be squared all the way up to sigma n. Or if you like, maybe it's better to just write this as, instead of writing them like that, we can assume that just the eigenvectors of this matrix and write them as lambda 1, lambda 2, up to lambda n. So this will be our matrix D, this matrix here. This will be the eigenvalues of this matrix. Of course, everything off the diagonal will be 0. So now, if I want to get the singular values, I will just give you the formula for that. Sigma 1 will be the square root of lambda 1, sigma 2, and so on will be the square root of lambda 2. It's the same thing I was writing earlier. I just thought I should get rid of the squares. And sigma, the last one was sigma n, should be the square root of the last eigen. So you can get the singular values like this. And then in general, if I want to get any of these singular vectors, left singular vectors, ui, the ith one will simply be the same as 1 over, pick the ith singular value, I, then a multiplied by the ith right singular vector, like that. So this will give me all the vectors for ui. Then it may not give me all the vectors because we said m is greater than or equal to n. But that will still work because now what will happen here is I will get the thin decomposition, the thin singular value decomposition. It's possible for me to extend the basis to make it a full basis. But I don't need to extend it because we don't need the other elements of the basis. So this will give me all the UIs I need. I will have obtained all the vectors V1 as eigenvectors of this matrix. And that will be done. So the other way you can do it, if you want to get the full, SVD, One way is to extend the basis to a basis for the whole space. Because this one, remember we said the matrix A is M by N. And we say M is possibly bigger. M might be bigger. So if you assume M is bigger than N, then by the time you get U1 all the way up to UN vectors, you'll have fewer vectors than the number of vectors you need to span the space in which this the space in which we get these vectors, the columns of the matrix A. So there'll be vectors of length M. So the basis for their space, they will be coming from the space Rm, but M is bigger than N. These vectors I'm getting will be fewer than N because M is smaller than N. So it won't give me a basis for Rn. I can extend it if I wish to get the full SVD, but we don't need it. And I've also not shown you how to extend the vectors. So, but there's a way you can get the full SVD. I think now instead of getting A transpose A, well, you can also get A transpose, and you get the so this I think will change. You will have sigma. Let me just call this sigma squared. Multiplying this by its transpose, just call it sigma squared to save time. I think you'll end up with something like this, but this now will be a diagonal matrix. So it will also be a diagonal matrix. So you can get these vectors U by getting the eigen decomposition of this matrix. But we shall not do this part. We shall just do this part. Get our eigen decomposition of the matrix A transpose A. You obtain the eigenvectors and make up V. Of course, we do orthogonal diagonalization so that this matrix is orthogonal. Then once we have all the vectors, the right singular vectors and the singular values, we can obtain all the left singular vectors, Ui, using this formula. Let's see if we can do I'll explain what you need to do. Then you will try to do this on your own. The complete working, you can do it in your own time. So that's the singular value decomposition. Essentially, what we are saying is that you have a matrix A, then you should be able to obtain all this. Will be quite easy to do on the computer. You'll be able to obtain a decomposition that looks like that, where this contains the singular values along the main diagonal, and U has the left singular vectors, and the matrix V has the right singular vectors. So the computer will be computing this for you. And once you have this, what you can do with this as a first application is to approximate a matrix. You say this is the same as sigma 1. Then you get U1 multiplied by V1 transpose. I think that was it. So you keep doing this until you exhaust all of them. If you wish to exhaust all of them, you'll go all the way up to sigma n, Un, and then Vn transpose. So this gives you the exact expansion. You will be able to recover A if you use all the matrices, all the terms. But if the terms are many, you can still get a good approximation by cutting off some of them. And one application of that is image compression. We shall see that in the application. So the example we have is here. These examples. Let's pick the matrix 1, -1, 3, then 3, 1, 1. So I think the important thing is to focus on this part. This is the part that we shall use. Maybe we'll start off with when doing the application. We'll also use the same ideas when working with the principal components analysis. This also is useful when working with the, what is the other thing called? I'll remember it. So let's first do the days. Where you're separating mixtures, I will remember. Forgotten the name. So there is a matrix here. What we want to do is to get its singular value decomposition. So what we need to find are these three matrices, U, sigma, and V. Then if you multiply them, we should be able to recover our matrix A. So this is now you'll be doing this to data also. Your data will be bigger than this, but this is exactly what you'll be doing to data. Data will be a matrix in the form of a matrix. So this is exactly what we shall be doing to it. For now, we pick a small matrix so that it's easy to compute. The larger ones you must do with the computer. So the first step is to find this product, A transpose A. You can try this in your own time and you should get the following answer. I have written it somewhere here. 10, 2, 6. Hopefully the calculations are correct. But that is just matrix multiplication, so it's something you can verify whether it's correct or not. Good. So now I need to diagonalize this. So the next step is to diagonalize this matrix. So what I need is to find a diagonal matrix which satisfies this property. I will have some matrix V multiplied by the diagonal matrix. And then I have V transpose. Since V is orthogonal, this is just the inverse of V. So essentially what I'm doing is I'm diagonalizing this matrix, which is here. So how do you diagonalize this? The first thing you do is to get the eigen vectors of this matrix. How do you get them? Minus lambda I, right? So you get the determinant of this, equate it to 0. You'll end up with a polynomial equation whose roots are the eigen values. So I don't have the polynomial here. I'll work it out later. But what will happen is you will get 3 eigenvalues. It will be a polynomial of degree 3, whose roots will be 16. The other root will be lambda 2 will be 6. And the other root will be 0. So this should be the eigenvalues of this matrix. Once you find the eigenvalues, you can find the corresponding eigenvectors, and then you normalize them. So the first eigenvector after normalization means you turn them into unit vectors. This is 1 over root 2 as the first entry here. Then we have 0 and 1 over. So we have 3 entries. So you'll get V2 after normalization, you will get 1 over root 3. So basically you get the eigenvectors and convert them to unit vectors. You might have different signs. Sometimes multiplying an eigenvector by a scalar, in this case, -1, does not stop it from being an eigenvector. So when you work them out, you can get different signs. So where I have positive, you might get negative. It is still correct, even if you do that. And the third one, the eigenvector, when you work this out, you should get 1 over. If you already know how to do this on the computer, maybe it's a good exercise to go and confirm that indeed this, although what we are writing here will be the exact -1 over square root of 6. So this bracket doesn't look very good. I hope my handwriting is legible. So this is a bracket here. So now you have the 3 eigenvectors. You can obtain so remember, in this case, we pick M. M in this case is smaller than N because it's a 2 by 3. 2 is definitely less than 3. So you only need 2. This will be a 2 by 2 matrix. That means you only need two left singular vectors. To get the 2 left singular vectors, you use the formula U1 is equal to 1 over sigma 1 multiplied by, then you get the matrix A multiplied by the vector V1. Is that correct? Yeah, I think it's correct. So we know the matrix A. We now have a vector V1. We know we haven't worked out the singular values, but the singular values are simply the square root of these eigenvalues. So the singular values in this case, you can say sigma 1 would be a square root of 16, which is 4. Sigma 2 will be the square root of 6. Is that correct? Yeah, I think so. If I wrote this correctly, it should be the square root of 6. We don't need sigma 3 now, but if you must write it, then that will be 0. So these are the values. Now you have the values of sigma. You have the vectors V1, V2, and V3. You also have the matrix A. Matrix A is here. So you can plug them into these equations. Now I'll leave that as an exercise for you. You plug them into these equations, 1 over sigma 2, V1, and then U3 would be equal to 1 over sigma 2, sigma 3. We don't need U3 because we have a 2 by 2 matrix here. U is a 2 by 2 matrix. Once you find these two are sufficient. And when you work them out and normalize the vectors, you should have something like this. U1 is equal to, the first entry is 1 over square root of 2. Second entry is 1 over square root of 2, again, the same entry. So that gives you the first left singular vector and the second left singular vector. Again, when you work it out, this is, and normalize it, you should get -1 over root 2 and 1 over root 2. So that completes everything. Now you have everything you need now to write out the. So U1 and you can write out A as the matrix whose columns are U1, U2. So you simply replace those columns U1 and U2 in this matrix, and you have your matrix U. Then you need the sigma. So sigma is what? Let's check. It has to be 2 by. Is it 2 by 3? I think, yeah. So what we have? Four and root 6. Uh, 0. And I think the last one now will just be a 0 code. Then on this side, we have the 3 by 3 matrix. Again, I won't write it in full. This side, we have the matrix, but this one is the rows of this matrix will be the transposes of this V2 transpose. But I think it should look something like this if I got it correct. But you get the idea. So this is U, this one will be sigma, and this will be the transpose of V. So I have turned the columns of V. V is supposed to be made up of the vectors U1, V1, V2, and V3. So if you get the transpose, these rows become, these columns become the rows. So what this means is that you pick the vector V1 and write it out here as a first column, pick the vector V2, write it out as a second column, pick the vector V3, write it out as a third column. Well, I think that's a good place to stop. So at this point, you should now be applying your knowledge of diagonalization. So there's nothing new here at this point. Once we get here now, it's just application of diagonalization once you get to this point. So the process is not always as straightforward as this. Sometimes you might have, there are a few other tricks that you need to complete the decomposition. But I think now the basic idea was for you to understand what is happening behind the scenes. But once you understand this, when we get to the computing, these matrices will not be confusing to you at all. Are there any questions? So you could actually knock out this 0 and also knock out the last 2 on this side. The last, not the last 2, the last vector on this side. Then it will still work. You will have a thin SVD. So are there any questions? So this is making use of a lot of the previous concepts that we did earlier. So if you had not taken time to master those previous concepts, this one now will not make a lot of sense. Like if you have not mastered orthogonal, this diagonalization, again, it will not make sense. Everything else is just manipulating the matrices to get to this point where you can do the diagonalization. In this case, orthogonal diagonalization. Once you get here, your work is done. The rest is just the eigen decomposition of this matrix.
May I ask a question?
Yes.
So well, let's pick a scenario where, let's say, we have an eigenvalue coming off as negative. What would be the significance of that, like when generating the U and V?
So this one is rigged. Your eigenvalues will not be negative.
There is no possibility of having negative eigenvalues?
Because this is a symmetric matrix here. So
I think
it might even be positive definite if I'm not wrong. But
the determinant of these two would be what? So hold on. No, that would be 0.
So they will not be negative.
Is there any proof for that?
Yes, there is.
I'll check the proof. Sorry.
I have avoided a lot of theory.
Okay.
So it's possible to prove that it might be necessary to work with a complex inner products. I don't know if we have time to go into complex inner products. Complex simply means you are, instead of working on the field R, your vector spaces now will be over the complex. Your scalars will be from the complex numbers. So complex does not mean complicated. It just means that your field, the field you'll be working with, is a field of complex numbers.
Yeah. So, but then, like, if you have a set, my worry was that, let's say, I was trying to understand the scenario where you have, let's say, one eigenvalue is positive and then the other one is negative, and your
you will not get that scenario. I'm telling you.
Yeah. I was struggling. Okay. So if all of them
you
are
will not get it.
Okay.
Yeah, there'll be non-negative. You can get a 0, but you will not get negative. So I think if you still need the details for that, we can arrange for the details on how to confirm that. I can try to write it out. I have avoided it because I don't think you need it so much on the application side. The application of this makes more sense for this course. If you had enough time, would have done the theory as well. So I don't know if that, I know you don't have you may not be fully convinced, but I think for now you'll take it as a gospel truth until I send you the details on why you cannot get negative eigenvalues. So, or is there a reason why you're asking about negative eigenvalues? Have you encountered a matrix where you got that? That would be strange if you got one. You can get negative eigenvalues, yes, but for this case, where this the way this is set up, you will not get them.
You said it's positive.
So pardon?
You said the matrix, that multiplication was yielding a positive definite matrix. And the eigenvector for the eigenvalues for positive definite matrix would be positive. Oh, but anyway, you can share them.
Yeah, that sort of brings out what we'll do. I think it's hard to put it in 1 or 2 lines. If you want the details, I think it's best to pick up the whole batch of details. So I will make arrangements for that.
Okay.
I can write it out and share the details on why that happens. I was avoiding, like I said, I was avoiding theory, because if we go deep into theory, that's the only thing we'll do for the whole semester. There's a lot. This is a very rich subject. Since most of the time you'll not be working with anything this small, or I mean data that is as small as this matrix. Where is my matrix? So most of the time your data will not be this small. It will be several columns and several rows, or maybe just 4 or 5 columns, but several rows. It will never be this small. So most of the time this will be done on computer. The basic idea here is for you to just understand the nuts and bolts. Once you have the nuts and bolts, when we go to the application, the application now should make sense because you've understood the nuts and bolts. I don't know if I made sense. I've tried to
Yeah, I
explain.
accept it. Yeah, my only worry was like just interpretation of how I thought that you could have a combination of real and complex vectors in real space and complex space in the event that you have the negative and positive.
You will not get them. It's basically this is a covariance matrix. This whole thing is essentially a covariance matrix, or if you like, a correlation matrix. Once you have standardized the variables. So in a correlation matrix, what happens? What is on the diagonal is the variances, right?
That's why you use signal, I guess.
And the variance,
I understand.
and they will all be, yeah, the variances will all be positive, or at least 0.
Okay.
Okay. If there are no more questions, we can stop there. I think I should stop the recording now.